don't know what to call them, and somebody comes up with a crazy name. Okay. Top and bottom. This used to be called truth and beauty. That was too good, so they changed them to top and bottom. Okay. Some of them actually are predicted and then found, and some of them are actually just found by, they're there, just there. Like the mu one, nobody expected it, just was found, and then they had to look very hard to really understand why it is there. So this we call the quarks, all right? These exist inside the nuclei, protons and neutrons in particular. These we call the leptons. These we call the leptons. From the Greek word leptons means light, and these we call, found inside hadrons, heavy. So these are the leptons, these are the quarks. Now, all of them, they have spin half. You know what spin is? It's an intrinsic angular momentum that is used, okay, to differentiate particles from each other. All fermions, they have half integer spin. Half, 3 half, 5 halves, etc. In this case, they all have spin half. That's the lowest spin you can have for a fermion. Okay? Yes.
So when you say that it's intrinsic property, does it depend on? Does it change when one quark decays?
No. Spin does not. Well, if they from ground state to ground state, we can have, for example, a charm going to down. Both of them are spin half. Okay, it doesn't change. It's just intrinsic property of the quarks. It's 1/2 spin, not total angular momentum. Okay, spin, the spin itself. Yeah, as an elementary particle, huh?
It represents angular momentum.
Yeah, it is an angular momentum, but it's an intrinsic angular momentum. When the particle is at rest, it has that much angular momentum. We call it the spin. Okay? These also, all of them have spin half. In addition to these, matter particles, these are the matter particles, as I said, whether it is stable, in which case it's made up of the first generation, or unstable, in which case it's made of a combination of the higher 2 generations. In addition to these matter particles, we have also particles which are the carriers of the forces, okay, between these particles. What are they? So we have the gamma that you're all familiar with. That's quantum of light. That mediates the electromagnetic force. The electromagnetic force, okay, which is due to the charge, electromagnetic charge. And then we have the W and the Z. We call them vector bosons, weak vector bosons. These, they mediate the weak force, the weak nuclear force. What is the weak nuclear force? The weak nuclear force is a nuclear force, definitely. And it is responsible for the decay of nuclei. It is the force responsible for the decay of nuclei. When you have a nucleus that is unstable, it decays by going to another nucleus and plus some radiation. Okay? So the force responsible for that decay we call weak force, and the carriers of the weak force are the W and the Z. And then we have the gluons, the G. The gluons are the carriers of the strong nuclear force. They are the strong nuclear force. What is the strong nuclear force? It is the force that is responsible for binding the quarks together inside the proton or the neutron. Okay? It's a force that acts to bind the quarks inside the proton or the neutron. Last but not least, we have the Higgs particle. As I said, it's still a mystery, and people are still really looking into it very carefully. But the Higgs really initially was introduced in the theory to give mass to these three vectors. All these carriers, they originate as massless. They don't have a mass. The gamma, as you know, The gamma is massless, okay? The photon is massless. So they are created as massless particles. The gluons are also massless. The W and the Z, they are not massless. Actually, they're very heavy. They are very, 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 very heavy. They are as heavy as a medium-sized nucleus. Very heavy. How do they get their mass? What? Through the Higgs. That's what gives them mass. And now we believe that the Higgs might also be responsible for giving masses to all these particles. Except the neutrinos. The neutrinos are massless. They are massless. They don't have mass. Or if it has, it's very, very little. But in the standard model that we work with today, they are supposed to have zero mass. Okay? Now, all these particles have spin 1/2, as I said. These guys here, they are 8 gluons, 1 gamma, and 2 W's, and 1 Z. These are all spin 1. That's why we call them vector bosons. Vector bosons. Boson معناها integer spin. Fermion half integer, boson integer, but they are vector. معناها they have spin 1. Okay, you can have spin 2, 3, 4, whatever, but in this case they have spin 1. Yes. Go ahead. What does it mean? Spin, as yeah, it's spin is a quantum number that each particle has. It's like it goes into, like U, for it. How do we know it's you? You have your height, your weight, whatever, color of your eyes. It's a property, it's an intrinsic property of a particle. It's an intrinsic property of each particle. Each particle has an intrinsic property we call spin that doesn't change. Sorry?
The spins of all these particles are the same as the electron, either spinning up or down.
If it's spin half, all these have spin half. Yani, as far as the spin is concerned, they're just like the electron. Yani, as you said, spinning up or spinning down. All of them. All of them. All the spin half. For the spin 1, it's different. There are 3 orientations.
Spin 1, you mean X1?
No, these guys. These guys are spin 1. There are 3 orientations. Okay? For Higgs, it's spin 0. The Higgs is a spin 0. It's the only particle in the universe. If it's elementary, maybe it's not. That's why they think it's not. It's the only particle in the universe which has spin equal, elementary particle, which has spin s equal to 0. There's no other elementary particle which has spin s equal to 0. Okay?
What does it mean spin equals 0?
And it's just a number. It's like temperature. It's a number. Or mass. It's a number. So to describe that particle, you only need a number. You don't need 2 or 3 or here you need 2 numbers, up and down. These you need 3 numbers. 3. Because spin 1, you have 3 possibilities. Okay? So you need 3 numbers to describe a spin 1 particle. Here only 1 number. 0. Yeah. No, not 0. I mean, you need 1 number. You just need the mass. That's it. Yeah, that's it. Okay, Shabab? So this is, now, there are other properties which you don't need to worry about, but what I'm going to take you now is through I wouldn't say an adventure, but historical survey of how we came about to do this. It's a very, I hope it's not a very rough ride, so I wouldn't ask you to fasten your seatbelts, but it's really interesting. If you like this subject, inshallah, it will be interesting to you. Okay? It's really a historical survey. And I mentioned the people, the particle one, where it was discovered, etc., etc. And all of them, without exception, they have all been discovered. As of 2012, that was the last one discovered. Experimentally. Okay? So it's not maybe, or they're all there. We know they are there. We have the proof. Okay? Khalas? So I will start with the particles first. Then if there is time, I go to the carriers, the spin 1. Okay, the particles, I mean, these guys spin half, and the Higgs as well. And it's very interconnected, by the way. It's really very, very interconnected. Theory and experiment in this case, they really go not only hand in hand. I think it's, I don't know how to call it, it's soul in soul. Really, they go together. Really, it's like one person with 2 feet. And so it's not like 2 people working in tandem. It's really it's one person. We call physics. It's one, yeah, it's one subject, physics, and it has one right hand and one left hand. We call theory, we call experiment. Okay. Sometimes you put your right foot first. Sometimes your left foot first. But this is how physics is done. Okay. This is how physics is done. There's no other way. Otherwise, we call it mathematics. Khalas? All right? So now I'm going to go and see how each one of these, I'll start with the electron, it's neutrino, mu1, it's neutrino, tau, it's neutrino, and then jump to up, down, s. These are together, and then charm and bottom and top. Once I'm finished with that, I go to these guys, and then the Higgs, and then the glue one. The gamma, we all know the gamma, okay? Gamma is, yani, I don't know, somebody discovered the gamma. I don't know, did anybody discover the gamma? Yes, of course. Yeah, the gamma, yeah, the gamma particle. Yes, there is, but we will see later on. Okay, let's start with the electron. As you all know, if you have taken any high school physics, okay? Huh? That's right. If you have chemistry, by the way, that's how, as I told you, it's Mendeleev, and so it reached this stage. This guy is J.J. Thomson. I don't know why the pictures look, well, maybe, yeah, it's some astigmatism. I don't know why. Really, I mean, on my computer, it looks fine. Yeah, that's maybe better. Okay, J.J. Thomson in 1895 or 1897. Okay, while playing with cathode rays, okay, you would generate your electricity, okay, in a gas. There is a gas inside this, and what he would do, he put a discharge inside the gas, and you see what happens. Okay, I don't want to say a lot about this because we have a lot to cover. So anyway, by playing with this for a couple of years, he found that actually atoms in the gas, they have something in them called electron. They have negative charge. So, and he was able to measure the charge to mass ratio, E over m. Now, we all know this, okay? We're having electric field and a magnetic field perpendicular to it. If you arrange them in such a way, okay, you can go straight. And only for a certain E over m, okay, you can get the electric force and the magnetic force to cancel each other. Okay? So this was really a proof that matter, atoms in this case, they have something in them that is very small, has negative charge, okay, has very small mass, that he called the electron. Alas, that was 1895. Now it's so simple, you can do it in, demos and labs like that. The second one is the electron neutrino. You would think, oh, it's very simple. The neutrinos, they have a very nasty property, and that they don't have a charge. The electron has negative charge. Okay? The neutrino don't have a charge. And something that doesn't have charge is extremely difficult to detect. Very difficult to detect. Okay? Not only they don't have a charge, they only interact weakly. They don't interact electromagnetically because they don't have a charge. They don't interact strongly, like the quarks. So the only thing they can interact through is the weak force. And the weak force is by definition weak. So if you have 30 Earths, Earths? You take 30 planets, the size of the Earth, and you put them one next to each other. and you have a flux of neutrinos going through them. You have a chance to have one interaction. One. So it tells you how weak the interaction is. So it's yes, 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 one. Even though, as we are sitting here, we have huge fluxes of neutrinos going through us. Amazing. You see the size of my nail here, fingernail? I have like 1 billion neutrinos going through it as you are sitting here. Hmm? Yeah. The universe is full of neutrinos. They're going through this way, this way, this way, this way. And we're lucky that the interactions are weak. Otherwise, you wouldn't survive for a day. Okay? So,
Even in other planets,
everywhere. Yeah. They are essentially uniformly distributed throughout the universe. Okay? Yeah. They are mostly, in our case, they mostly come from the sun. The heat of the sun, the light of the sun, is produced through weak interactions. Okay? And whenever you have a weak interaction, neutrino comes with it. So these neutrinos are produced at the sun, and they reach us, okay, in very large quantities. Okay? So, only in 1956, not very far back, was the electron neutrino identified. Okay, and they had to do it next to a reactor which has a huge neutrino flux. Actually, they found antineutrinos, but it's all the same. Okay, on the Savannah River. Okay, Frederick Reines, this guy, he got a Nobel Prize in 1995. This guy died before that, so he wasn't awarded the prize. Okay, so it took very long time. The neutrino was expected to exist. It was actually postulated by Pauli, another famous physicist, but there was it was postulated because of some conservation of energy and momentum. Okay, when you have the decay, energy and momentum are always conserved. These are sacrosanct conservation laws. And you needed a third particle to make up for the loss of the momentum that you noticed, okay, that you observed. So he said there must be a third particle, and he called it a neutrino. That third particle had to have spin half, and it had to be massless. And that's the neutrino. It was discovered in 1956. So it's very, very late, because it's very difficult to detect neutrinos, yes.
Did Pauli expect it to be charged? Did Pauli expect
No. Neutral. We knew it. No. It had to be neutral, massless, spin half. Okay?
compensate for what?
For the loss of momentum. When they have a decay, when you add the initial momentum of the particle and the final momentum, they're not equal. Okay? Khalas? So that does it for the first generation leptons. Yes. Let me show you. Yeah, no, actually, yes, they detected it, not as through a reaction. This is the reaction that detected through. Okay, this is the reaction. Okay, they have antineutrinos coming from the reactor. They hit protons in water, essentially, and you get neutrons and positrons. What they detect is the neutron and the positron. This they detect, they know. And these two can only come if we have this reaction. They cannot come from any other reaction. Yes? It's an independent particle. Huh?
Other than electron? Or
yes, other than the electron. Yes. Okay? Why electron? Because it only happens when there is an electron or positron involved in the reaction.
That's why it's called electron.
Yes, exactly. Yeah. Okay? Now we go to the next generation, the heavier one, the mu1. Remember, there is electron neutrino, mu1 neutrino. Yes? Question? tau and tau neutrino. Now let's go to the mu1 now. Okay? The mu1, when it was, as I said, it was found in cosmic rays. And the guy who found it, Carl Anderson, and with his student, Seth Niedermeyer, from Caltech at that time, this guy got a Nobel Prize, oh, actually both of them, because he was responsible for the discovery of the positron in 1932. In 1932, okay, and a couple of years before that, Dirac predicted the existence of antimatter. Dirac predicted the existence of antimatter, which is completely revolutionary, very revolutionary. Okay, so he got a Nobel Prize in 1936 or 1936 for the discovery of the positron. He's the same guy who identified the existence of muons from cosmic rays. Okay, so he got these cosmic rays. They interact with something they called, I think it's some kind of detector, some kind of chamber. I'm not sure what the name is. Yeah, cloud chamber. It's called the cloud chamber. Okay, and they have a specific, they have a signature. Okay, they have a signature. Okay, that signature is indicative of the existence of a muon. Okay, the muon comes from cosmic rays. It hits, there's a lead here, it's lead, and then it enters a cloud chamber. Okay, the muon, of course, as I said, is just a heavy version of the electron. It's a heavy version of the electron. It's 207 times more heavy than the electron. Otherwise, in all other aspects, it's exactly like the electron. Okay? It's a heavy version of the electron. All right? So it is not stable. It decays to the electron. The electron is the next stable particle, so it decays to it through this process. Okay? Have mu1 it gives mu1 neutrino, and then it gives an electron and an electron antineutrino. Okay? على كل حال. So this is the mu1, 1936. 1936. Before the detection of, remember, electron neutrino. Electron neutrino was detected in observed in 1956, 20 years after this. I mean, this picture that I showed at the beginning, that was the result of painstaking efforts of thousands upon thousands of very brilliant, hard-working physicists. Really, it's amazing. It's both theory and experiment. Okay. And it decays to an electron in essentially 2 microseconds. 2 microseconds. Okay. What's next? The mu1 neutrino. The mu1 neutrino. So now we finish the second generation of leptons. The mu1 neutrino. Yeah. Okay? So the mu1 neutrino was discovered using accelerators at Brookhaven National Lab. That's where I used to work. Okay? And one person who was in this work, Gordon Denby, I knew him personally. We have publications together. Okay? But these guys, when he worked with them at that time, they got the Nobel Prize for this discovery. Okay? They got it in 1988. But the work was in 1962. So the mu1 neutrino was discovered in 1962. And for this work, they got the Nobel Prize in 1988. Okay? So Leon Lederman, very brilliant, I know him also, very brilliant physicist from Columbia. This guy didn't know, Melvin Schwartz and Jack Steinberger. He was almost 100 when he died. 100 years when he died, essentially. Okay. He died very recently. These two guys, they died some to 2018. He had Alzheimer, and they had to sell his Nobel Prize medal to pay for his expenses. He had Alzheimer's disease, so his family put him in home care. Okay, it was very expensive, and health insurance in the U.S. is a nightmare. Okay, health insurance companies did not want to take him under health insurance, so they didn't want to pay. So they had to sell his medal, maybe for $700,000 or something, to pay for his expenses. على كل حال. So this is the muon neutrino, discovered in 1962. So it is 6 years after the electron neutrino. Now they have experience, but this was detected in a different way, not the same way that the other guys. The other guys detected it using antineutrinos from a nuclear reactor. These guys, they used particle accelerators. So it's like, yeah, it's different. It's different. Okay? Yes, sir.
Why is particle elementary?
It's elementary in the sense that it's not made up of something.
But they decay simpler.
It decays to a lower energy or lower mass particle, yes. It's unstable. It decays through the weak interaction. It decays through the weak interaction to a particle of lower mass. Like the mu1 here, mu1 neutrino is, well, this is what you are saying applies for the mu1. For the mu1 neutrino, it is massless, essentially massless, so it doesn't decay. It does not decay, okay? If you believe it's massless.
Recent experiment shows something else, right?
About what?
About the neutrinos.
The mass.
Electron.
Yeah, this comes, I'm talking about within the standard mode. Yes, now there is reason to believe that they have very small masses, and therefore they are responsible for what you call neutrino oscillations. Neutrino oscillations, okay? But it doesn't change much, okay? So this is for the second generation of leptons. Second generation of leptons. Third generation and last of leptons starts with the tau particle. Okay? The tau particle is very heavy. It's supposed to be leptons, yani light. Actually, it's heavier than a proton. It's 1.7 GeV. A proton is roughly 1 GeV. So it's almost twice the mass of a proton. It was discovered in 1970s, I think 1977, I think, by a group of people, and he was probably the guy who was responsible for the experiment. He got a Nobel Prize in 1995, almost 20 years after the discovery. His name is Martin Perl. And you see, it decays with a half-life or the lifetime of 10 to power minus 13. So which is, well, it looks very small, but actually it's quite long. It is quite long. It's indicative that it's a weak process. It's a weak decay process, okay? And it decays to a neutrino, tau neutrino, and then electron antineutrino, or mu1 antineutrino, or to D and the U bar. D is the D quark, and U bar is the antiparticle of the U quark. Okay? So that's the tau. What's remaining? Tau neutrino. Okay? Question? No? Tau neutrino, it's probably the only neutrino that actually they had the whole experiment set just to detect it. Probably among other things, but just to detect it. That's why they call it donut. It's the detector for the observation of a new tau. Donut, detector for the observation of a new tau. New tau is the tau neutrino, exactly. Okay, and it's called the D0 donut collaboration. It was discovered at Fermilab in Chicago, okay, in around 2000, around 2000. So it's not very far back, about 20 years ago. So this is evidence for the existence of a new tau, okay? And as you can see, the number of people involved starts to increase. As the experiment becomes more and more complex, what does it mean? It means the detector has to be more and more complex, okay? And here maybe it's 50 people. You can see later on, I didn't even didn't have place to put it. You can easily have like 500 people, easily, okay? Like you have today in CERN, easily 1,000 people, okay? So that's the neutrino. And that's the paper announcing the discovery of the tau neutrino, okay? That's the paper. It was in Physics Letters B, okay? All right, any questions? So now we are finished with the leptons. All the leptons have been discovered. Electron, electron neutrino, mu1, muon neutrino, tau, tau neutrino. Khalas, finished. Now we go to the quarks. طيب. The problem with the quarks is that we believe they cannot be observed individually. Not only cannot be observed, cannot exist as individual quarks. They can't. Okay? Why? We don't know. But we believe that. We have reason to believe, of course. It's not just it's not ordained, just we have reason to believe. We have reason to believe that we cannot observe frequency. Because a lot of experiments have been done to detect quarks. All of them are failures. Nothing was discovered. Okay? So, how did we get to know about quarks? To learn about them, to think about them, to believe that they are there. It's a long story. So I'm not going to, because I'll come back to it a little later if I have time, but for many reasons, the up, down, and strange quarks, okay, were more or less, their existence were inferred for the three of them, okay, for the three of them, not for the up alone and the down alone and the strange alone, okay. So the quarks, they can be classified into two categories, really. The up, down, strange, these are what you call the light quarks. And then charm, bottom, and top, these are the heavy quarks. So the up, down, strange, these are the ones that make, or up, down is what makes stable matter. Strange, still, it's heavier than the up and the down, but still it's light compared to the other ones. Really, it's different mass, factor of 10 almost difference. So let's start with the quarks. Good. Quarks, the idea of quarks was first introduced by somebody called Murray Gell-Mann, whom we will see again because he was very active at that time, very bright physicist. He was the Mendeleev of particle physics. Just like Mendeleev was very important to chemistry, Murray Gell-Mann was very important to particle physics, really. In the 60s, he was really at the top. Now, they were introduced by him, but nobody really believed, few people believe that they are really real, that these quarks are real. They thought it was just a mathematical artifact because they were introduced, the idea of quarks was introduced to make sense of the plethora of particles that existed at that time. So all sorts of particles were being discovered. And to classify these particles into groups and subgroups, okay, he came up with the idea that particles are made up of either three quarks or a quark and an antiquark. Those particles which are made of three quarks, he called baryons. Those particles which are made of quark and antiquark, were called mesons. And once that's done, and you believe that the symmetry that governs this classification is SU3, don't worry about that, then really a lot of very good classification comes about. Very good, excellent, okay? So yeah, it's really the particle physics community was divided now, and some people believe that yes, quarks must be real, and some people said no. I mean, unless we have real proof, they're just mathematical artifacts. Until 1968, there was a series of experiments from 1968 essentially to 1974 at Stanford Linear Accelerator Center in Stanford, okay, headed by these three guys from many institutions, but headed up. They did essentially what Rutherford did. How did Rutherford infer the existence of a nucleus? How? Huh? Yeah, so he had atoms, doesn't matter what atom really, it's gold nuclei or whatever, and then he shot charged particles at them. Why was he led to believe that the atoms are made of a very dense and small and massive nucleus surrounded by electrons? Because if the atom was diffuse sphere of negative and positive charge, the scattering of the charged particles through the atom will be essentially in a very narrow forward angle, okay, just multiple scattering. However, if you believe or you think of the atom as being made of a very small nucleus, positively charged, surrounded by a cloud of very light electrons. Electrons at that time, we knew they were very light from the work of Thomson and Millikan. Then there is a probability, small but not zero, probability that some of these beam particles will scatter back at very large angles. Okay, you shoot particles at the target. Most of them will make it through, but every so often, some of them will go back to you, and they come back and hit you. That was an indication that the nucleus was very small, positively charged, and very massive. That's the only way you can get these particles back. Okay? They did essentially the same thing. Okay? Essentially the same thing. But instead of a nucleus, they use now a nucleon. They have electrons hitting protons. Electrons hitting protons. So if the proton is a diffuse positive charge, you will see the scattering of the electrons essentially forward within a small angle. But yes.
They were hitting hydrogen plus. They were hitting pure protons, H plus.
Yeah. Proton is water. I mean hydrogen gas, and they remove the electrons from it. Okay. Okay. And then they saw the same thing. Instead of this forward scattering, they saw electrons coming back at them. And when they did the calculations, it's very technical. When they do the calculation, they found out that you had to have three centers, three separate centers inside the proton. Not one, but three. And they did it with the neutrons, same thing. They saw that you needed three dense centers inside the neutron or the proton to explain the scattering of the electrons from them. Okay? And this three was the first indication that we have quarks inside protons and inside neutrons. Three. That three was firm. It's not it's not something maybe two, maybe no, it's three. All right? So that was a landmark experiment, okay, which gave a lot of faith into quarks, believing that quarks indeed they do exist. It's not just a mathematical artifact. Okay, I'm sure that Murray Gell-Mann was very happy to hear that. And they got a Nobel Prize for this in 1990. Again, almost 20 years after their work was finished. Okay, and that's the paper that they published their work in. All right? Essentially from two places. One is from the Stanford, as I said, with R.E. Taylor, this guy. And the other guys, Friedman and Kendall, from the MIT, from Massachusetts Institute of Technology. Okay? So this was really the first experimental evidence for the existence of quarks inside nucleons. In that case, protons and neutrons. So that's it's a landmark, really, paper. So yes?
Can I ask about the strange quark? Was it found in the same process?
Of course, they use protons and neutrons. These guys don't have strange quarks in them. Okay. But the strange quarks was needed to explain the existence of other particles. Okay? And I will come to it. It was discovered. I don't mention it here, but what happens is when Gell-Mann was classifying these particles, coming up with this scheme, he predicted the existence of a particle which was not known at that time. It's called the omega minus. The omega minus. It was discovered in 1964, actually, in 1964. Okay? With the properties that he predicted for it, like the mass and the isospin and the spin and all that. So that was a strong indication, but still not direct proof. So when they found that there is actually direct proof of the existence of up and down, that for strange came like a byproduct, okay? Because it explained something that we observed, but it's not a direct evidence for the strange quark existence, okay? Fine. So up, down, strange, finished, more or less. I could say more, but it will take some more time. But inshallah, if there is a second version of this talk, we'll say more. Now, what's the next quark? That's the beginning of the heavy quarks. Charm, bottom, and top. The charm quark. Now, all these quarks, especially the charm and the bottom, as I said, the quarks cannot be seen individually. They don't exist as individual quarks. They can only exist as individual quarks inside the proton and the neutron and other particles. But outside, they can only exist as a baryon or as a meson. In this case, these guys, one from MIT, one from Stanford, they detected through some experiments. They were not looking for this charm. They were just looking what's there. Okay, and what they see is whenever they hit a mass, the energy range, close to the mass of this meson, so CC bar is the bound state of a charm and an anti-charm. A charm and an anti-charm. This we call charmonium. Charmonium, okay? Like positronium, E plus E minus. Charmonium is the bound state of a charm quark and anti-charm quark. Okay? This guy, they discovered the particle and they call it the J particle. For some historical reasons. He's a Chinese American, born in the US. And he's actually a graduate from the University of Michigan, where I graduated from. Okay? Burton Richter was from Stanford, and he called it the psi. He called it the psi. So now it's called the J psi particle. But when they looked at their findings, it had exactly the same properties. The J particle and the psi particle had exactly the same properties. Okay, so they decided to publish their papers on the same journal, the same day, the same issue. You see, number 31, I guess, 33, volume 23, December, 2nd of December 74, 2nd of December 74. So one paper after the other. So they publish at the same time. So nobody will get credit as getting funding in first. So they want both of them to get the Nobel Prize. Okay, so experiment. This was done at Brookhaven under the leadership of Ting. And this guy, they did the experiment at Stanford. Okay, so experimental observation of a heavy particle, the J, discovery of a new narrow resonance in E plus E minus annihilation. Okay, they have E plus E minus, they hit each other. Okay, and then some matter is created. Okay, this guy Y.Y. Lee, Brookhaven Lab, because I worked at Brookhaven Lab. I know him personally, very well actually, and we have some papers together also. All right, so there you go. That's the charm quark. And the energy of the charm CC bar, the energy is around, I think, 3.75, something like GeV. Okay? So finish with the charm. What comes next? The bottom quarks. Well, essentially, it's an extension of what was done, essentially an extension of what was done for the charm quark. Again, we see Professor Lederman, okay, heading a group of people, okay? And they observed a bound state of a BB bar. This was done, I think, at the Tevatron, if I'm not mistaken, in Chicago. Let me see. Yeah, Fermi National, yeah, at the Tevatron, okay? Fermi National Accelerator Laboratory. The group at Fermi Lab was headed, at Columbia at least, was headed by Leon Lederman. There are many other people, okay? But it was like a repeat of what was done with the charm. Exactly the same thing, okay? And this BB bar is called an upsilon, okay? It's not the other guys, they called J psi. This guy called it upsilon, okay? Upsilon. And that's the paper, 1977. 1977, okay? What comes after the bottom quark? Yes? The top quark. Now, the top quark, you would hope that, yeah, just like the CC bar and the BB bar, you would be able to create a TT bar. The problem is, oh, the bottom quark, the charm quark was about, I think, 1.7 GeV, if I'm not mistaken. The bottom was like 5 GeV. So it was still possible to create a BB bar, which is twice the mass. TT bar, the T is 175 GeV. It's way, way, way heavy. So you cannot create a bound state TT bar. You cannot create it. Just as soon as it's created, it decays. So how do you detect the existence of a top quark? Through the decay products. Through the decay products. And that's how you do it. And the top quark was actually identified through its decay products in two experiments, the CDF collaboration and the D0 collaboration, both of them working at the Tevatron in 1995. Okay, again, it's the same paper, the same journal, one after the other. But there was no Nobel Prize awarded, neither for this nor for the bottom quark. The charm was the first one, okay, of the list of the heavy quarks. They got the Nobel Prize. The others, sorry guys, okay, it was already done, khalas. Now I'll just show you here a quick picture to show you the complexity of the detectors, okay? This is the detector of the CDF detector. This is the D0 detector. And these are huge, really. These are really huge. I mean, it could be easily be as big as a classroom, full, big classroom, okay? So it's very, very complicated, very complex, and very complicated also. So finish now with the quarks and the leptons. You have time? Huh? Should I continue? Okay. The next particle that I want to talk about is the Higgs. So the Higgs, I'm going to say very little about it now. If I have time, I come back to it, okay? Because I just want to finish it now so that I finish with the particles, okay? Because it's a particle after all. I mean, it's a particle, what I mean, of course, all of them are particles. But I have it here, well, it's the Higgs. Now, it has a long story, the Higgs. As I said, we'll come back to it, inshallah, later on when we talk the forces. the weak force. Okay. I didn't have time to put all the details of this, but just the detection. This is the last of the elementary particles detected. It was detected in 2012. Okay. In 2013, somebody was awarded the Nobel Prize, the guy who predicted it. I will talk about it in a minute. But it was found by, again, two experiments. One is called the Atlas detector, and the other one is the CMS detector. Both of them at the LHC, Large Hadron Collider, at CERN. You see now how physics has moved to, the Center of High Energy Physics has moved to Europe. It was in the United States before. Fermilab was the highest energy accelerator. Now it is CERN. Okay? This girl here, her name is, I just found her name. I don't. She's the spokesperson. She's relatively young, really. She was in 1960. So she was only 40. She's now maybe 60 something. Still young by, you look at the people. To be the spokesperson usually of a major experiment like this, man, you have to be good. To give you some numbers, this is the detector, the Atlas detector. It's a multi-purpose detector. It has 46 meters long. 46 meters long. I don't know how big this room is. Maybe as big as this room. Huh? So it's almost 50. And then 4.25 meters wide. Okay? It is 100 meters below ground. Okay? To shield against cosmic rays. 100 meters below ground. It is 7,000 tons. 7,000 tons. Okay? So a car is about 1 ton, roughly. Medium-sized car is so that's like 7,000 cars. Okay? And it has 1 billion collisions per second. 1 billion collisions per second. So you can imagine how much data it will collect in a day. Okay? And how much software you need to sift through all this data. It's amazing. You take data for 3 months, you spend 3 years analyzing the data. No joke. 3 months data, 3 years to analyze. Okay? And then you start publishing. So that's, yes? Yeah, this is, the LHC is a PP accelerator, proton-proton accelerator. Each proton has 7 TeV energy. So the total central mass energy is around 14 TeV. That's the highest energy accelerator ever built. It cost about $10 billion to build. Okay, it uses superconducting magnets, and they need super fluid helium to cool to very low temperatures. And one time they had one of the coolants was punctured, and all the helium escaped. And just to empty the whole thing and start fixing it and filling it again with superfluid helium, it took like 6 months or something like that. So it's really big. It's amazing.
Also, America tried to build a bigger collider than this.
Yeah. I was there when that was happening. The SSC, it's called the Superconducting Super Collider. Yes, that was a big flop, unfortunately. Yeah. They built the tunnel in Texas. Now they grow mushrooms in them. Literally, they grow mushrooms. It's a good. So this woman is the spokesperson for the Atlas detector, and this guy, I think he's of probably Indian origin, British Indian, and he's the spokesperson for the CMS detector. CMS stands for compact muon solenoid. Okay. And they detected the Higgs particle at 25 GeV. Again, the Higgs cannot be detected also. It's very unstable. And what they see is the decay products. The decay products, okay? And from that, they reconstruct the mass and the half-life and all that for the... So this finishes now the particles. The lepton sector, the quark sector, the Higgs sector, okay? And now all experiments are about studying the Higgs particle, the decays and everything. Okay. Ready? Khalas? Relaxed? You need 2 minute break? Should I continue? Huh? Okay. Oh, okay. So now I move to the carriers of the forces. The carriers of the forces that are taking place between these particles, between the quarks and the quarks, between the quarks and the electrons, and the quarks and between these particles among each other. Now, as you know, there are 4 forces in nature that we know of: gravity, electromagnetism, weak nuclear, and strong nuclear force. Okay? Now, electromagnetism, actually the physics is not so much in the particles. The particle is just like, really, it's like a stamp collection more or less. It is spectroscopy. Just look at the particles and classify them, and it's like a zoo, you know, the bears together and the lions together, and then after that, what do? You look at them and go to sleep. The real stuff is in the forces. That's what the real physics is. I mean, it's like astronomy, you know. You have planets. You look at the planets. People have looked at planets for thousands, at least hundreds of years. Okay, they classify them. You have Uranus, you have the moon, you have the earth, you have the sun. But the real breakthroughs came when how they interact with each other to predict, you know, when you will have sun, what do you call them, eclipses and whatever, okay? That's the really, when Newton found his law of gravitation, that was a real breakthrough, okay? That was the real breakthrough. Now, QED, called quantum electrodynamics, has its roots in classical electrodynamics. That much we know. Now, who started classical electrodynamics? Maxwell, exactly. So Maxwell really is the, if you want, the grandfather of quantum electrodynamics. I would say just the grandfather. It really starts with Maxwell. Okay? It started with Maxwell. Okay? In 1865, he wrote his equations. What do these equations do? First of all, of course, he built upon the work of Faraday mostly, and then before him, Coulomb and Ampere and all these guys. But also his genius was to combine all the work of Faraday, which, you know, Faraday has, if you look at the library, he has a book of his experiments. There is not a single equation. It's all description, you know, English. There's not a single equation. And the genius of Maxwell was that to translate this English into equations. It's amazing. Okay? It's really amazing. So he started with Maxwell. What did he do? He described the interaction of electromagnetism and of charged particles with each other through electromagnetic field. That's what he did. Okay? And he put these equations, and it works. So really what he did, in a way, he's unified electricity. At that time, magnetism was one branch, electricity was another branch, and optics was another branch. He said, okay, guys, it's all the same. Electricity, magnetism, and optics, it's all due to electromagnetism. Okay, that was really something. All right? He didn't live very long. Otherwise, probably he would have made other breakthroughs. He wrote his first paper at the age of 14. He entered the university, I think, at the age of 15 or 16 or something like that. The next breakthrough really came again through another. Maxwell was Scottish. Dirac was British with some French blood, I guess, because from his name. Okay, this next breakthrough really came with Dirac. Now here I'm jumping over the period when quantum mechanics was developed. He was also a major player in development of non-relativistic quantum mechanics, but more in particular, the formulation of relativistic quantum mechanics and the quantization of the electromagnetic field. You see, at that time there were two things. We have electrons, matter يعني, described quantum mechanically, but non-relativistically. On the other hand, we have electromagnetic field described classically, but relativistically. Electromagnetism is relativistic by nature, all right? But it's classical. So he needed to do two things. He needed to come up with a relativistic formulation for the motion of the electron. That's his Dirac equation. And he needed to come up with the quantization of the electromagnetic field. And he did both. Once he did both, the road was now all paved for quantum electrodynamics. So he's really the originator of quantum electrodynamics. And while doing that, he had to invent antimatter. If you describe something relativistically and quantum mechanically, you are led to believe, you are led to invent antimatter. You cannot have a consistent theory of quantum mechanics of relativistic particles if you don't include antimatter. You can't. Okay? At that time, what antimatter was, I mean, it had the electron, the proton, and the neutron. That's it. But even the neutron was not discovered yet. So it was simple. You just multiply by 2. You have 2 particles, electron. Okay, you have positron. Proton. Okay, you have antiproton. It was easy. Okay? So it wasn't a big shock. But essentially, that's what he said. Okay? To every particle, there exists an antiparticle with the same mass, opposite charge, and opposite angular, same spin also. Okay? So this is paper. It's called the quantum theory of the emission and absorption of radiation. This is what we teach when we do time-dependent perturbation theory. That's exactly all taken from this paper. The problem is this. He, of course, and other people with him, when they used this theory, his theory, to do some calculations, they're hitting a snag. What was the snag? They get infinities. You calculate a cross-section, it's infinite. You calculate a decay lifetime, it's infinite. You calculate anything, it's infinite. So many people of his generation, they gave up. The quantum electrodynamics is not a consistent theory. And they said, we have to think something else. And things stayed that way for 10 to 15 years, okay? Until a new generation came along, a new generation. Okay, some of them were young, like these 2 kids at that time. They were really very young at the time. And an older person, Tomonaga from Japan. They said, no, these infinities can be taken care of through a process we call renormalization. Okay, it's very technical, so I will not say anything about it. It's really technical. Essentially what it does in a systematic, rigorous way, isolate all the infinities of the theory and put them in quantities that are not measurable. And all the measurable quantities now are finite. That's what it does. Okay? Isolate all the infinities and put them in quantities that are not physical, they're not measurable. So don't care what they are. And all the quantities that you care about, that you can measure, are finite. The process of doing this is called renormalization. And they did it. Okay? And they did it. So they saved quantum electrodynamics. Really, they saved it. Okay? And for that work, they got the Nobel Prize in 1965. Okay? And these are some of the papers. These are the early papers that published. One by Tomonaga, one by Schwinger, and one by Feynman. Okay? QED is saved. So this is the first success, and it's the most successful theory in physics. The reason why, it calculates something we call the anomalous magnetic moment of the electron. Essentially, it's the ratio of the magnetic moment to the spin. Okay, it's a number we call gyromagnetic ratio. It calculates it to 13 digits. 13 digits. It's like 0.000. Huh? 13 digits. It agrees with the experiment. So that cannot be coincidence. Okay, cannot be a coincidence. So it must have a great deal of truth in it. Okay, and it's the most successful one. It's so successful actually that the weak interactions has been essentially copy-paste from this, and the strong interaction also essentially copy-paste from this. Because it was so successful, it worked, said, okay, if it works, let's try to do the same thing for the weak interaction and do the same thing for the strong interaction. And that's what they did. And guess what? Except for some difficulty, of course, it's no new level of difficulty, but it works. Now we know all of them, QED, the weak interaction and the strong interaction, they are derivable from something we call the gauge principle. The gauge principle, okay? And it's the last beautiful idea of physics that we have. And it dates back to the 70s. And that's it. After that, no more bright ideas in physics. High energy, yeah? We have something else, Allahu A'lam. But in high energy, string theory, supersymmetry, all that stuff just didn't work. Okay? Maybe in the future, but now they have a problem. QED, khalas. So what is it now? This is the successful quantum description, quantum relativistic description, okay, of the interaction of electrons by the exchange of photons. That's what it is, okay? You have charged particles, essentially electrons, okay? They interact with each other through the exchange of virtual photons. And it works. Beautiful. And it's quite simple, actually. It's not very complicated. The next force that we will talk about is electroweak. Now, electroweak, in a way, is really the story of weak interaction, is the story of particle physics in some ways, because it took 50 years to finalize. Okay? Once QED was established, essentially QED was well established by 1950. By 1950, everybody was convinced that QED is a good theory to have. Okay? Then started the work on the weak interactions. But before that, there was an attempt the first attempt at a successful theory of a weak interaction was actually by reproducing or using the tools of QED to weak interaction what was done for electromagnetic interaction. And the first attempt was by Fermi. Okay? Enrico Fermi. Probably you all have heard of him. In 1934, he published a paper called On a Theory of Beta Decay, an attempt to a theory of beta decay. Nobody wanted to publish his paper. So he sent it to, I think, Physical Review. They rejected it. He sent it to somebody else. They rejected it. Probably, I don't know. So he sent it to Il Nuovo Cimento, which is any low-rank journal. We call low-rank these days. Okay? And it was published. He also sent it to a German journal called Naturwissenschaften. So it was published there also, in German. He knew German. He knew English, a little bit. He knew French, probably a little bit. Of course, he knew Italian. That's his language. So it was published there. Okay? He got a Nobel Prize in 1938, not for this. He did so many things. He was one of the best physicists of his time, period. He was really one of the best. Okay? He knew almost everything in physics, about everything. You give him any problem in physics, he will do it. He was the guy responsible. This was his last, it's not the first, but his was last theory paper. His last theory paper. After this, he turned to experiment, and he was responsible for the whole program of nuclear fission using neutrons, okay? And he developed the first nuclear reactor in the United States in 1941. Okay, he was the man in charge. He was in charge of the whole program, and also he was in charge of the program at Los Alamos to build the nuclear bomb. He was also heavily involved in that. Okay, he died very young, probably because of the neutrons that he used. Actually, they got the better of him, and I think he died, I think, of stomach cancer, because he was working with radiation a lot. Okay, he was working with a very brilliant group of people. Okay, some of them, one of them at least, Emilio Sigri, was also a Nobel Prize winner afterwards. He co-discovered the antiproton at Berkeley. Okay, with Owen Chamberlain. Anyway, so he started, the first step at a successful theory of weak interaction was by Fermi, 1934. 1934. Now, hold this date in your mind because we'll come back to that. You see, 50 years later, we had the complete theory of weak interactions, not before. Weak interactions are known to be, or not known actually, they were forced to assume that they were parity violating interactions. There are some symmetries in physics which are satisfied by all interactions. Okay? Parity was one of them. Everybody believes, of course, parity must be conserved. It is conserved in weak electromagnetic interactions, no problem. So they assumed it was conserved in weak interactions as well. But when you do that and you look at the experiments and the data that you have problem. One way to get out of this problem is to assume that weak interactions are parity violating interactions, not parity conserving. Now that was really a revolution. Nobody thought about that. Okay, physicists take this conservation laws very seriously. Okay, you can't just go and say, oh, it's not. They take them very seriously. And these two guys, Yang and Lee, they were very young at that time. Okay, he did his thesis with Fermi. He did his thesis with Edward Teller, another brilliant physicist. They're very old, still alive, subhanallah. Okay, they published a paper in 1956 saying, question of parity conservation in weak interactions. So they're suggesting in that paper that parity is not conserved. 1 year later, because just after publishing this paper, another Chinese woman, T.D. Wu, I think her name was, from Colombia, she did the experiment and proved that parity was actually violated in weak interactions. So that immediately they got the Nobel Prize. 1 year later. He was 30, he was a little over 30. So very young. 1 year after their paper, they got the Nobel Prize. I think this is probably the shortest, or I'm sure one of the shortest periods, because sometimes you get at least 10, 15 years before they give you a Nobel Prize for your work. 1 year. Because the experimental verification was almost immediate. And when they finished their article, when parity was proven experimentally to be violated, immediately they wrote to Pauli. Said, yes, you were right, neutrino exists and all of that. And he was really happy to hear this. Okay? Yes? Huh?
In cases like this, do the experimentalists who discover or prove the theory also take the Nobel Prize?
Yes, she did. She did. She did. Because it was the first of a kind. You have to do something that nobody did. If you do it again, you will not get a Nobel Prize. That was something. That was the measure. So this is the second important step. The first step is the work of Fermi. And essentially what we do now is a refined version of what Fermi did. Okay? Fermi theory does not allow for parity violation. Okay? So parity violation in weak interaction was the second major step. Was the second major step. Okay? The third major step was what we call now is to say that weak interactions are actually a form of, they derive from a gauge invariance. Okay, just like QED. QED can be formulated to be derived, essentially. You derive the interaction term in QED through a gauge invariance principle. Gauge invariance, what it is? In QED, gauge invariance is symmetry, and gauge symmetry is responsible for the conservation of electric charge. Just as invariance under physical displacement is responsible for the conservation of momentum, linear momentum. Just like when you say invariance, invariance of the Lagrangian, invariance of the Lagrangian. So invariance of the Lagrangian under time displacement is responsible for the conservation of energy. Okay, you can prove that. We do this in physics 300. Okay, so gauge invariance or gauge symmetry is responsible for the conservation of charge. That's what gauge symmetry is. And QED, and when you say QED, you say the interaction term of QED can be derived without knowing anything about it, can be derived from the imposing gauge invariance on the Lagrangian. If you impose gauge invariance, you immediately get the interaction term that you know is right because you already have a classical analog to compare to. Okay? So these three guys, this is what they did. Okay? This is what they did. Steven Weinberg, Sheldon Glashow, this guy I know, came to Michigan many times. And this is Abdus Salam, okay, from Pakistan and England. Okay? So they formulated this weak and the electromagnetic interaction. So when you do that, when you do derive weak interactions through a gauge invariance, you need, you must, you have to put it with electromagnetism. Okay? You put it with electromagnetism. What we call now electroweak theory. Yani they are like, yani if high energy, it becomes one theory. Yani one theory. At low energy, it breaks into two branches. One is electromagnetism, and one is weak interactions. So weak interaction is really like electromagnetism. That's why, as I said, when you do this, على كل حال, it's a long story, but this is what they did. This is what they did, okay? This is what they did. Sheldon Glashow, very early on, he wrote a paper. And then before him was Abdus Salam and Ward. And 1967 paper by Steven Weinberg was probably the most convincing one, called The Model of Leptons, is one of the highly cited papers in particle physics. Okay, 67. So what did they do? They derived the weak interaction through a gauge invariance principle. Okay? And they had to put it alongside with electromagnetism for that. That's beautiful. And they got a Nobel Prize. So they predicted the existence of, just like electromagnetism is mediated because of the gauge nature of the theory is mediated by a massless photon. The gauge formulation of weak interactions requires the existence now, the existence of three vector bosons: the W plus, the W minus, and the Z0. And they have to be massless. But we know they cannot be massless. If you put a mass in the Lagrangian as ad hoc like that, theory cannot work. We have to put them massless. But we know they are not massless. So how can they get mass without having a mass? That was the problem. That was the open question at that time. But it was, they knew they were in the right direction. But there was a problem. How to give masses to the W plus and the W minus and the Z? How to give them masses while saving the mathematical structure, the gauge structure of the theory. Okay? Now comes the Higgs. This is why the Higgs was introduced, for that specific purpose. Okay? So that's 1967 for that specific purpose. These three guys in 1964, around that time, okay, Francois Engler and Robert Brut from Belgium, and Peter Higgs from Scotland, from Edinburgh, just like Maxwell. Okay? Many years later, almost 100 years later. Really, 100 years later. This guy died, so he couldn't get a Nobel Prize. So this guy got a Nobel Prize. This guy got a Nobel Prize in 2013. That was the Higgs mechanism. We call the Higgs mechanism. It is a very complicated anyway, but many people worked on it. But these two were distinguished for one reason or another, so they got the Nobel Prize for that. And now we have a scheme, we have a scheme or a mechanism called Higgs mechanism to give masses to the W plus, the W minus, and the Z0. The question was, the new theory now, is it renormalizable or not? Yani, if I do calculations, will I get infinities or not? Because if I get infinities, it's useless, completely useless. And if I don't get infinities, I have to prove it. That came 5 years later by two very bright people. Yeah, it has to be alive. It has to be alive. They're not that generous. Yeah, yes. He did just 2 years before he died. Subhanallah. هذا كل أرزاق. Yeah. Now came these two people. One of them is Martinus Veltman. He was my teacher. I took 2 courses with him, one in quantum field theory, one in group theory at Michigan. And this was also one of his early students, Gerard Hooft. Both of them are from Holland. In 1972, they published 2 papers showing, without any ambiguity, that the new theory of weak interaction, actually we call it electroweak interactions, okay, with the Higgs mechanism is renormalizable. And it becomes a respectable, acceptable theory. Before that, it wasn't. It might be good to look at, might do some calculations, but you have no proof that it is an acceptable theory. They did that, and they got the Nobel Prize for it in 1999. Okay? Martinus Veltman. He died recently, actually. He's a very no-nonsense person. He's not very sophisticated in theory, but he's very, very good. Because he has his 2 feet on the ground. He doesn't want to speculate too much. He wants to do real calculations. He is the first one who has written a code called Skunskip that does symbolic manipulation, symbolic calculations. Symbolic, you give him calculation, he does it symbolically. He gives you like what you call Mathematica, okay? But at that time, it was the first of its kind. He developed it when he was at CERN, probably, or in the US, I'm not sure, okay? But it was, maybe I should have worked with him when I was there. I didn't. I was an experimentalist, okay? So this very, very important step, very important step. Now we have a complete theory. What is missing? Yes? Sorry? Well, I can hear you. No. Oh, gravity is another area. It's another. We need to find the Higgs. Is the Higgs a true particle or is it fictitious? Because we need the Higgs mechanism to give masses to the W and the Z. But does the Higgs exist? Yeah, that was in 1972. Remember? 1972. That's the paper. Since that time, the They were hunting for the Higgs. And it was discovered in 2012 because they needed, because the Higgs is a very, very muddy, murky area. It's not like the W and the Z. They were predicted with the masses that they were found at. Exactly. Okay? No ifs, no buts. But the Higgs, wishy-washy, okay? Wishy-washy. Maybe there, maybe here, maybe it doesn't exist. Allahu alam. But the last piece of the puzzle was, before the Higgs, I'm sorry. Yeah. Guess what? We have to find the W and the Z. The gamma we know. The W and the Z, are they real? Huh? Are they real with the masses that the Higgs mechanism gives them? Yes. Yes. They were found in 1983. Okay? By a very large group of people. So it's useless to put the names. But the Nobel Prize was awarded with these two guys, Carlo Rubbia. Okay? I was at Brookhaven when he came and announced the discovery of the W and the Z. And Simon van der Meer, he's an accelerator physicist. He invented a mechanism to increase the intensity of the antiprotons. Because these were found in proton-antiproton collisions. And the antiprotons, as you know, they're produced with very low intensity. So he had to invent a mechanism to increase the intensity. It's called stochastic cooling. Stochastic cooling. And it works. And they got a Nobel Prize in 1984. So 1 year after. Again, it's very short. The W plus, W minus, and the Z were found as essentially the exact masses that they were predicted to exist at. And they got 1 year later, they got the Nobel Prize. The experiments that is called the UA1. It's called underground area number 1, UA1, underground area number 1. Okay? That was a very large, sophisticated detector at that time. And they had the same thing, UA2 detector also was repeated. They found the same thing. Okay? It was confirmed. You know why they need 2 experiments to look for the same thing? Yes, it's very important. It's very important. Because, because if they find the same thing, chances are very high that it's true. But if any one of them finds something different, both of them be wrong. It's very important. It's not just for fun. It's to confirm, as you said, independent way, not the same way. Independent way, yes. It's independent way, yeah, independent way, okay? It's not just to repeat. It's not just to repeat. To look at different angle of the same process. And okay? So
there could be an additional parameter where different ways could be proposed. How
doesn't here actually what they're looking at as the decay products. Okay? Decay products, these particles are very, very short-lived. And you detect them through the decay products, okay? Or something like that. The decay products are many. There is many channels. So one detector will be optimized to look at one channel, or 2, or 3, or 4, and the other detector will be optimized to look at the different channels.
So we are looking into a single channel that we are looking for.
No, not a single channel, a single event. But the results are, there are many outcomes. Okay? Many outcomes. You look, one detector is optimized for a certain decay, for example. Another one is optimized for a different decay from the same event. Okay? If both of them, they reconstruct and they found that the particle responsible for this channel and the one responsible for this channel has the same properties, the same half-life. Yeah, then yes, exactly. So it's an independent confirmation. Yeah. Khalas, W finished. So the Higgs now is missing. That was 1983. Okay? It was big news at that time. Oh, I don't have the Higgs here. Okay, somewhere else. So I will show it later. Okay, here is the Higgs. Oh, I showed it before. Yeah, this is the Higgs. Okay, I showed it before. Okay, that's the Higgs. It came in 2012, so it came very late. Very late. 50 years after it was predicted, or 40 or something, 64. So 60, 40. 50 years. 48 years to be precise. 48 years after it was predicted. Okay? It required a lot of energy. Now, is this the whole story? Well, not at all. Not at all. Weak interactions are responsible for many things. Okay? One of them, one process that exists in nature, we know, and weak interactions are responsible for it, is called CP violation. Yani, P is for parity violation. We know weak interactions are also parity violating. There is a theorem in quantum field theory, any quantum field theory, that says that, called the CPT theorem, charge, parity, time. If you take a particle, do a charge conjugation on it, yani antiparticle, then you invert the time and the space, okay, then the laws, the Lagrangian doesn't change. It's a rigorous theorem, first proven by Pauli. This is responsible for what you call the spin statistics theorem and all that, okay? Pauli exclusion principle. Fine. We know parity is conserved. Parity is violated in weak interaction. We know that, and we have a theory that explains it. But you also have CP violation. Very rare events, not many, but very rare events that not only violate parity, but also violate charge conjugation together at the same time. Very rare. And it's a very active field of research now. The real reason why we don't know, but at least to explain some of the events we observe, that are CP violating events, okay, we have to do something. And that something started a long time ago, but essentially, so as I said before, we start with Gell-Mann with the existence of the up-down and strange quarks, and then this is the paper in which he proposes his scheme of classification. And then this is all theory. I'm not talking about the discovery of the charm. This is why the charm was predicted to exist. That was the first paper in 1970, 70-something. Yeah, 1970. Okay, these three guys, Glashow, very active at that time, Iliopoulos, and Mayani. Mayani was here one day. I remember he gave a seminar here. I was sitting there, and okay, and he gave a seminar in Meridian Hotel also. He was the director of CERN at some point. Okay, very bright physicist, Italian. They wrote this paper called the GIM mechanism, Glashow, Iliopoulos, Mayani mechanism. And that mechanism was needed to explain why some events are not happening, why some decays don't happen, or happen with very low probability, even though they are allowed, but they don't happen. Okay? They are suppressed. And what they predicted was that if you now, in addition to the up-down strange quark, you have a fourth quark called the charm quark of the same type as the up, only with charge 2/3, then you can explain now why these events are suppressed. Okay? So just, not predicted, but they just said we need a fourth quark, the charm, they call it the charm quark, okay, to explain why these events are suppressed. Okay? And as you know, this was in 1970. When was the charm quark detected? Remember? Charm quark, 1976. Not long after this. The J psi particle, remember? The J psi, yeah, that was 1975. So not long after that, it was discovered. Okay? So that's one thing. A more important thing for CP violation, these guys, they took upon themselves to extend the GIM mechanism. You know the GIM mechanism I just talked about? They said, let's extend it now. Let's not only add one quark, add two quarks, the top and the bottom. If I have two quarks in the third generation, okay, then I can explain why some CP violating events are taking place. So to explain CP violation, okay, we needed to have the bottom and the top quarks. And these two Japanese guys are the ones who suggested the existence of the top and the bottom quarks to explain CP violation. And that's their paper. Okay? CP violation in the renormalizable theory of weak interaction. Now we have a renormalizable theory of weak interaction, remember? Because of all the work, starts with Fermi, and then Yi and Li and Yang, okay? And then Weinberg and Glashow and Abdussalam, and then what? And then the Higgs mechanism, and then the renormalizability by Veltman and 't Hooft. You see how many? Over so many years. Now we have a complete renormalizable theory. They said, if use the same theory, but now with an extended family of quarks, increase the number of quarks now to 6 instead of 4 as before, then I can see where CP violation is coming from. Because with 4 quarks, you cannot have CP violation. You cannot have. With 6 quarks, you can. Okay? And that's their idea. And for that, they got a Nobel Prize in 2008. Okay? Where am I? Yeah. So now, we have a weak interaction, or you should say electroweak interaction. Okay? The W and the Z discovered. What is remaining? The Higgs discovered. The Higgs was needed because of the W and the Z, remember, huh? To give mass to the W and the Z and keep the theory renormalizable and mathematically consistent. What is remaining now? The strong force. The strong force is remaining. We didn't talk about the strong force. You have time for that? I don't. I have a little bit of time because it's getting late and I didn't have time to prepare the whole thing, but I will say something. Yeah, if you need part 2, I can give part 2. Huh? Yeah. Let's give it to part 2 because I did not do a good job preparing for the strong interaction. Because it's not easy, by the way. It's not easy. The strong interaction is, from 7,000 places you have to look. Because it's a long story. Huh?
I do have like some theoretical questions about the types of Higgs boson.
The times?
The types.
Oh, the types. Now we assume there's only one type. In the standard model now, one type would do. But you are right. It could be more than one. Is it a bound? Maybe it's a bound state. Maybe it's not just an elementary particle.
This is another question.
Yes, exactly.
It's a part 3.
No. These things are active areas of research. So I don't have answers for them, really. Yeah. I cannot give you final answers because I'm not working in them. I know about them, but I'm not an expert in these things. Okay.
I'm not looking for final answers. The world doesn't have a final answer.
No. What I'm saying, I'm afraid I will not be able to give you a definite answer, yani expert answer. Okay. Yeah, I can guide you, maybe, but to give you a firm professional answer, maybe not. Maybe not. But it's an open field of research. The whole LHC work now is on the Higgs sector. It's called the whole sector, and it's there. So we'll, inshallah, if we are still around, we inshallah schedule part 2, okay? And we call it the history or brief review of strong interactions. So we start from all the way back to nuclear reactions, from Hideki Yukawa, okay, to the pions, to it's a long story. It's a long, also very fascinating story. Okay, in some ways it overlaps, and with what we did here, but because the same people you see here, sometimes you see them here, sometimes you see new people. Okay. But the idea is this. What are the ingredients of the strong force? The quarks, it's one ingredient. Because these are the only strongly interacting particles, are the quarks and the gluons, only. All the others are not strongly interacting. So we need the quarks, we need the gluons, and with the concept of color, okay, which is an extra degree of freedom, okay? And we need, I don't know if we need, but we have to talk about what we call asymptotic freedom. Asymptotic freedom is a property of QCD, okay? The structure of QCD allows for asymptotic freedom. What it says is that as you go to higher and higher energies, the theory, the strong force becomes weaker and weaker. And therefore, you can apply perturbative calculations, okay? Perturbative calculations. And that was the last, probably the last breakthrough, not say breakthrough, but the last major contribution to strong interactions, and by three guys, Gross, Wilczek, and somebody, not forgot the name. I think they got the Nobel Prize in 2004. That was the last major work recognized as such. So it's still QCD is very complicated theory, and it's still very fertile ground for new things. And it's very difficult to work with. Very difficult to work with, really. Very difficult.
Will be really generous, the second part is the
I will try. I will try without making a fool of myself. Okay, Shabab, thank you very much.